Hey class, today we're going to go over lecture 33 about pH and tie in some of the concepts that we've been learning uh, about acids and bases here. All right. Go ahead and pause the video and try this question out. Okay, so this one says, if lemon juice has a hydronium concentration of 6.3 times 10 to the negative third molar, what is the OH minus concentration of the solution? So we should be able to use this idea that we talked about in the last lecture, that Kw equals hydronium ion concentration times OH minus concentration, and that is equal to 1 times 10 to the negative 14, right? And rearranging that to solve for OH minus would give us this equation right here. Okay, and then we plug in our Kw value, so 1 times 10 to the negative 14. Plug in our hydronium concentration from the problem, and we can solve for OH minus concentration. Okay. All right, so in the last lecture we talked about this relationship, right, where in a neutral solution we have an equal amount of hydronium ions and hydroxide ions. In an acidic solution we have more hydronium than hydroxide, and in a basic solution we have more hydroxide than hydronium. Okay, so the pH scale is going to reflect that relationship that we just talked about. It's used to indicate the acidity of a solution. So pH is a number, okay, and they generally range from 0 up to 14, okay, and that's the pH scale. So if something is less than 7, so closer to 0, then it's going to be acidic. If the pH equals 7, we say it's neutral. And when the pH is greater than 7, then it's a basic solution. Okay, so you might be wondering, like, why is it 0 to 14? It's kind of a weird scale. Why is 0 to 7 acidic? Why is 7 to 14 basic, right? So we're going to talk about the reasoning behind some of these numbers, tie it in, and it should start to make some sense. Okay, so Kw equals 10 to the negative 14, which we talked about. And so here's a table that shows the different pH values starting with 0 all the way up to 14. And it shows hydronium concentration and hydroxide concentration at each of these pH levels. And what you'll notice is that the exponent in the hydronium concentration always mirrors the pH number, okay? So this gives a reason on why the pH scale goes from 0 to 14, right? Because the highest hydronium concentration we can have is 10 to the negative 14, right? Because hydronium times hydroxide equals 10 to the negative 14. I guess it's not necessarily the highest, but anyway, for our purposes, that's as high as we're going to go. And yeah, anyway, okay. So, yeah, that's the highest the exponent will go. Okay, so this pH tells us, like we just noticed here, what the exponent of the hydronium concentration is. So hydronium concentration equals 10 to the negative pH, right? So you can see, like, pH of 3, hydronium is 10 to the negative 3, okay? So that's where this equation comes into play. In this equation, we're going to come to, this is basically the one equation. Well, there's two equations, but the other one's derived from this that we're going to learn in this lecture, okay? All right, here's just another relationship that you can see. You can see, like, OH minus concentration. So 14 minus the pH, you'll see that in here, 14 minus pH equals the exponent for OH. So like pH 14 minus 9 would equal 5, basically, or 14 minus 11 equals 3. Okay, just another relationship, but don't worry about that equation as much. You don't really need that one too much. Okay, let's go ahead and try this quiz here and see how we do. Okay, it says some brands of root beer have hydronium concentration of 10 to the negative 4 molar. What is the pH? Okay, so in the last slide, we learned that pH is going to be the exponent of the hydronium concentration, right? Since we have a 4 here, pH would be 4, okay? And again, this is negative pH. So it's not that the whole exponent is the pH, just the part after the negative sign is the pH, okay? All right, so now we're going to talk about calculating pH. So far we've said, like, if the exponent is 4, then the pH is 4, right? That's really simple. That's if we say that the hydronium concentration equals some power of 10 molar, right? Well, what if the hydronium concentration isn't a power of 10, right? Usually we see concentrations like this, something weird, 1.35 times 10 to the negative 4 molar, right? Or 7.32 times 10 to the negative 4 molar. Okay, so this is where we're going to derive basically a new equation. We're going to use logarithms because we talked about how pH is equal to the exponent here, and in order to solve for exponents, we need to use logarithms, okay? All right, so just hold on for 1 second while we derive this equation. So this is the equation I said that's important to know up to this point, right? Hydronium concentration is equal to 10 to the negative pH. Okay, we learned that from that table. Okay, so then if we take the log of both sides, this is what comes out, okay? Don't worry about all the math and stuff. I mean, you can look at this if you want, if it's interesting. But the other equation that I want you to know is pH equals the negative log of the hydronium concentration. So these two equations are really the big ideas from this lecture. Okay. So for a solution with any given hydronium concentration, we can now plug it into here, put it in our calculator, and use the calculator to solve for pH so that we can find the pH for any concentration, right, without doing tons of math. We just can put it in our calculator. Okay, so for this example, pH equals the negative log of the hydronium concentration, which is given here as 1.35 times 10 to the negative 4. The log of this right here equals negative 3.87. And we have the negative of the negative. That switches your sign. So our pH equals 3.87 here. You'll notice that since this is almost 1 times 10 to the negative 4, the pH is almost 4, which is what you'd expect using the kind of the basic rule that we learned at the beginning of the lecture. All right, go ahead and try this out on your own. Okay, so here's another brand of root beer that has a hydronium concentration of 3 times 10 to the negative 5 molar. What's the pH? So we know that pH equals the negative log of the hydronium concentration. So we can plug the hydronium concentration in here, solve that on our calculator, and our calculator would, well, just the log of 3 times 10 to the negative 5 gives you negative 4.52, okay? And then we have the negative of that, so you switch the sign and get 4.52. Cool. All right. So one thing I just want to point out, if that problem didn't work out for you, here's just some information about calculators, but make sure your calculator log button is what you think it is. Sometimes when you see log, it's actually a log base E. Some are log base 10, but we need to use the log base 10 button on your calculator. So make sure you're not using the ln, which is the natural log. I think on most calculators, it's going to be log. But anyway, the way you can test it right now is grab the calculator you're going to use for the exam and put in log of 10, and it should equal 1. And log of 100 should equal 2, and log of 1,000 should equal 3. As long as you're getting those, just remember what button you're pressing to get those, and that's the one you're going to want to use when you do these calculations. Okay. Okay, so why pH, right? Why the little p? What does that mean? So you'll find out that there are a lot of different values that start with p that we're mostly going to deal with pH, but you'll see a lot of pKa especially. The pKa and pH are the two big ones that you're going to see in organic chemistry. pKb is rarely used. POH is also rarely used. But they all have one thing in common, right? The pH is the negative log of the H plus concentration, right? That's why it's called pH. POH is the negative log of the OH concentration. pKa is the negative log of the Ka. pKb is the negative log of Kb, right? So the P stands for power, or the exponent, right? So in all these cases, we're using this to solve for the exponent of the concentration if it was a base 10. And that's all where it comes from. Anyway, you don't need to memorize, I mean, you do need to know the pH, and at this point you should probably know POH is a negative log of the OH minus. We're not going to talk about pK and pKb right now. I'm trying to remember if we even get to it in this class, but I'm just pointing out that whenever you see P something, it's just the negative log of whatever that thing is. Okay. All right, go ahead and try this problem. Okay, so this says a solution has a hydronium concentration of, 1 times 10 to the negative 3. What's the pH? Okay, so the answer is B. Well, they're all the same, right? So just kind of, at this point you might have been guessing, sorry about that. But let's talk about significant figures when we're doing the pH calculations, okay? Okay, so here's the rule. When you're doing logarithms, and specifically with the pH calculations, however many significant figures you have in the concentration number is going to be how many decimal places you have in your pH. Okay, so if you're doing the pH of this number, we have 2 sig figs here, so our answer is going to have 2 decimal places. Okay, so just remember that rule. One more little rule to add to your significant figure calculation rules there. All right, go ahead and try this one using that newfound knowledge. All right, so if you put it in your calculator, that's great to get the practice, but you can see these are all pretty much the same number, just different significant figures. So here we can see we have 3 sig figs. Oops, 3 sig figs, which means we need 3 decimal places in our answer, right? So that should be C. Okay. Let's go ahead and try this one out as well. All right, so the OH minus concentration of a solution is 1 times 10 to the negative 3. What is the pH? All right, so we've talked about pH is equal to a negative log of the hydronium concentration. Well, we're not given hydronium concentration in this problem, but we also know that the hydronium concentration and the hydroxide concentration together equal 1 times 10 to the negative 14. So that tells us that we can, like we did in the last lecture, using OH, we can solve for the hydronium concentration. Divided by OH minus. Okay, and then we can solve for hydronium. So we have this number, we pop it in here, the calculator pops out the hydronium concentration, then we pop it in here, and we can solve for pH. Right, and then this number has 2 sig figs, so it's going to give us 2 sig figs for our hydronium concentration, which means we need 2 decimal places in our answer. Okay, here's just PowerPoint walking through it. Okay, so the answer is going to be 11.00, 2 decimal places. All right, another quiz practice question to help you as you go through the homework here. All right, what is the pH of a 0.15 molar solution of calcium hydroxide? All right, taking even more steps back here. The question is asking for pH, so we know we're going to use the pH equation, which is the negative log of the hydronium concentration. But we need hydronium, right? All right, you might be lost right now, Best thing to do if you're lost on a test or homework or anything is just start writing down what you got. So we have a 0.15 molar solution of calcium hydroxide. Okay, so calcium hydroxide, this, and it's a solution, so it's placed in water. And when that happens, this is a strong base, so it should dissociate into calcium ions and 2 hydroxide ions. Okay, all right. Now, again, using the same equation from last time, we can solve for hydronium concentration using the fact that hydronium times hydroxide concentrations equal 1 times 10 to the negative 14. Okay, but we need the hydroxide concentration. We have the calcium hydroxide concentration, and so what we could do is we know that the calcium hydroxide concentration is 0.015 molar, which means we have 0.015 molar, or sorry, 0.015 moles of calcium hydroxide in 1 liter. And now if we want the hydroxide molarity, we need to convert this moles into moles of hydroxide. So for every 1 mole of calcium hydroxide that's dissolved, we have 2 moles of OH minus, right? So that tells us that we have 0.030 moles of OH minus divided by 1 liter. And by definition, that means we have a 0.030 molar, that pen's lagging, molar solution of OH minus, and then we can pop that into the equations. All right, let me have the PowerPoint show it a little cleaner. Okay, so again, this solving for the OH minus solution using the stoichiometry here, we can then plug OH into this equation here, which spits out the hydronium concentration, which we can then pop into the pH equation and get the answer. Oh, sorry. Back up. Okay, here's another alternative down here. I don't like this one as much. I think it's kind of confusing. So if this made sense to you, just move on. But if it didn't, you can go through a lot of math derivations and come up with the fact that pH and plus POH equals 14. So if you're given the hydroxide concentration, you could solve for POH and say 14 minus whatever POH is equals pH. So it's another way to look at it, but I think it's easier just to kind of memorize the as least as possible and just work off of that. Okay. All right, let's go ahead and try this one. Okay, so if you remember, out of the 2 equations I said were most important from this lecture, one of them, the first one, was that H3O plus concentration equals 10 to the negative pH, right? Well, we have the pH here, so H3O plus equals 10 to the negative 10.0, right? And then, so that pretty much rules out A, rules out B, and it rolls out E, right? So now, because you can see we have 10 to the negative 10, which is just 1 times 10 to the negative 10.0, right? So we just need to know how many decimal places should be at this 1. And we have 1 decimal place on the pH, which means we have 1 significant figure in the concentration. Okay, so that should be C. Okay. Alrighty, we're zooming along through these last lectures. Each of these lectures doesn't seem to like have a ton. Well, it looks like a lot of information, but hopefully I boiled it down. Like in this lecture, those 2 equations I pointed out are really the big ideas. And then knowing the pH scale goes from 0 to 14. And then you'll see that At 7, the hydronium and the hydroxide concentrations are equal, and you have a pH of 7. And then as the hydronium concentrations increase, your pH actually goes down, and as they decrease, your pH goes up. Anyway, hopefully some of the homework problems will continue to like reiterate these ideas as you're working through them. So, all right, we'll see you in the next one.